Hello everyone and welcome back to Physics with Mr. McQueary. Today's lesson is on Newton's three laws of motion, and this happens to be probably the least entertaining of things that usually come in threes when you compare that with the Three Stooges, the Three Blind Mice, or even the Three Little Pigs. Our target today is being able to describe Newton's laws of motion and then relating them to real-world situations. And the idea is to give you a situation and be like, okay, which one of Newton's laws is most relevant here? Those kind of questions. Newton's first law is sometimes called the law of inertia, but the actual definition is an object at rest stays at rest, an object in motion stays in motion unless there's an unbalanced outside force that comes in contact with that. That's a mouthful. Let's break that down a little bit. Basically, things are going to keep on doing what it was already doing unless something comes out like an unbalanced force and either changes direction or it changes motion, right? Basically, if you're going to be still, you want to remain still, and if you're moving, you want to keep moving. So these unbalanced forces are basically when you have a force that is not balanced out by another one, hence the name unbalanced. For example, when you're in free fall, it's an unbalanced force because the only force acting on you is gravity. But consider like a textbook sitting on a table. That is a balanced force because you have the normal force and gravity canceling out. That's a balanced force. So that's not going to change whatever motion your object's already in. Some examples from all life include a soccer ball. When it's just sitting there, it doesn't want to change its motion. It requires a kick, aka an outside force, to change its motion, to speed it up. Or this little puppy right here, sliding along on the ice. He's going to keep sliding on that ice until there's some other outside force that slows him down. Maybe someone sprinkles a little salt on there for him to give him some friction. Like we said before, Newton's first law can also be called the law of inertia. And inertia is just basically a tendency of an object to not change what it's currently doing. So if it's at rest, something that has a lot of inertia is really hard to get moving. Or if something's already moving and it has a lot of inertia, it's very hard to stop it from moving. And all objects have inertia because inertia and mass are directly related. The more mass you have, the more inertia. Less mass, less inertia. For example, of the objects over here, one of them has the most inertia. Obviously, it's the elephant. An elephant is the hardest to get moving. If you've ever tried it before, it probably didn't end well for you. Or even worse, if you try to stop one, that's really hard to do, right? The other ones are much easier to change their motion. Other examples include this guy right here. He had all that rock. When he stopped, that rock slid forward. It wanted to keep on moving forward, but the truck stopped, so it just smashed into the back of it. Or this guy over here who's trying to flick looks like a paper football. And the paper football doesn't have a whole lot of inertia, so it's easy for something that's already at rest for him to quickly accelerate it with just a flick of a finger. So the rock has a lot of inertia, paper football, not so much. If objects in motion tend to stay in motion, how come we just don't have objects moving forever and ever? Well, there's almost always an unbalanced force that acts upon it, right? Think about this guy who's sliding over here. His unbalanced force is friction. That's why he's not just continuing to keep on sliding. Or over here with Rafiki and Simba, you know, the reason why Simba doesn't keep flying forever and ever is because gravity is going to bring him back down towards the Earth. This is seen in outer space. For example, the Voyager missions, we sent out actual spacecraft, and they just keep flying off deeper and deeper into space. And because there's limited gravity and there's limited friction, there is still gravity. Let's be honest with that. Let's make sure we don't forget that. But because it's limited, it appears to keep on going forever and ever. Now, eventually, it will slow down, right? That's as close as we can get to something with truly balanced forces. Newton's second law is one equation. The sum of all your forces, when you add them up, is equal to mass times the net acceleration of the system. Now, an easier way of saying that is F equals ma. Let's do some practical applications here. On the right, we've got The Rock and we've got Kevin Hart, one of the better comedy duos in Hollywood right now. Now, Kevin Hart is about half of the mass of The Rock. So if they're both accelerating at the same rate, then The Rock is going to be having twice as much force as Kevin Hart. And you can see there some math to back that up. Now, let's put that in perspective a little bit. If Kevin wants to have the same amount of force as The Rock, then he's going to have to accelerate twice as fast. You can see we used F equals ma to set this up, and we set them equal to each other to solve for acceleration. You know, there's some things you can do to this equation. If you double the mass, you're doubling the force you exert. If you double the acceleration, you double the force you exert. If you double both of them, you're actually going to quadruple. Right? So it's a direct relationship. You cut the mass in a third, for example, then your force you're going to be exerting is about a third. Likewise with acceleration. If I multiply by 10, then your force is going to be multiplied by 10. So what you do to one side, I have to go to the other side. A couple other things here, just real general. You can have some crazy things happen with force. For example, something as massive as a glacier with a huge amount of mass can have a very, very small acceleration, but still exert a lot of force. Likewise, something very small, like a bullet, for example, with a massive acceleration can still have a very high force. So there's, it's not one size fits all. Sometimes it's a very high mass that gets you force. Sometimes it's a very high acceleration that gets you high force. So we have 4 different balls here. If we apply the same amount of force to each one of those, which one's going to have the greatest acceleration? It's going to be 4, right? Why? Well, if you want a higher acceleration, then you need a small mass. Likewise, if you want a large mass, you're going to decrease that acceleration, right? Newton's third law says that for every action, there's an equal and opposite reaction. It rhymes, but let's go a little deeper into it. Take, for example, maybe you're sitting in a chair. When you're in that chair, you probably don't realize that there's a force acting against you. Sure, it makes sense that the gravity from our weight is pushing on the chair, but we don't fall through that chair, thank goodness. There's a normal force that pushes back against us, and that's why you don't accelerate in either direction. For example, let's say Isaac Newton over here slaps the roof of his car. The car would slap back at Isaac Newton. Now, I know it's a meme, but yeah, really, when you slap something, it slaps back at you a little bit. Maybe not with a hand like this one, but you're going to feel it. That's why your palm might be a little sore afterwards. Think about a couple things. What happens if you're standing on a skateboard, maybe a slippery floor surface, and you push against the wall? And this guy right here. Obviously, you're going to be pushed back the other direction because while you're pushing on the wall pushes back on you, and you start sliding. Practical application of Newton's third law. So is this guy when he runs into the wall. Ouch, that hurts, right? And it hurts a lot because the force that he exerts on the wall exerts back. Equal and opposite reaction. Now, let's just say sometime in the future you're in outer space. You're just out there floating, but you want to get back to your ship. There's a way you could use Newton's third law to make sure that occurs. You take maybe, for example, your wrench you have that's handy on you, and if you throw it to the left, equal and opposite says that you're going to start moving to the right. Now, obviously, because you have a larger mass than that wrench, you're not going to accelerate as fast, but you'll still experience the same force. This is a video here that talks about equal and opposite forces in football.
One of the things we study in physics is the interaction between objects. Check out this interaction between these objects. Great job, guys. Now, you felt a greater force in that interaction.
Well, I guess I did.
Well, actually, according to Newton's third law of motion, that states for every action there's an equal and opposite reaction, you both felt the same force. Let's demonstrate with the scales. Now, it's safe to say you're stronger than me, right?
Yeah.
All right. But it doesn't matter how hard you pull. On your scale, my scale reads the same number. What's true for pulling is true for pushing. You and Corey felt the same force.
Well, how was I able to blow my line?
Well, there are other force pairs involved, namely between you and the ground. You push it against the ground, and the ground pushes you forward. If you push the ground harder than the other guy, you move him back.
Cool. So I guess that's why Coach told us to keep our feet moving.
Exactly.
All right, let's demonstrate that.
Whoa, wait a minute.
In summary, Newton's three laws of motion states that the first law is the law of inertia. The second law, F equals ma, and the third law, for every action, there's an equal and opposite reaction. A couple of vocabulary terms that might come in helpful is inertia, which is the tendency of an object to resist change in a state of motion. We found before that the greater your mass, the greater your inertia. The smaller your mass, the smaller the inertia. Acceleration is any change in velocity, whether that is your magnitude or your direction. Acceleration can better be more likely be defined in an easier way of how quickly an object is changing speed or direction, or both. Velocity, well, that's kind of how fast you're going per unit time. And force, that's your strength or energy. Some people will say a push or a pull. These are examples of Newton's laws of motion. Right here we can see that clearly that we're using the equation F equals ma. So this corresponds to the second law. The force of the nail on the hammer is the same as the hammer on the nail, Newton's third law. This guy wants to keep on going, even though the car stopped. That sounds like inertia, Newton's first law. The cannon, when it fires that cannonball, is actually blown backwards a little bit. It's an action-reaction pair, Newton's third law. When you exert the same force on two different objects, the one that's larger has a smaller acceleration, like the car. And the bag of potatoes, since it has a smaller mass, will accelerate more. Sounds like F equals ma, sounds like Newton's second law. Last but not least, you're standing on a subway train. The subway comes to rest, but your body continues forward because that's the way it was already going. Sounds like inertia, sounds like Newton's first law. I hope you've enjoyed today's discussion on Newton's three laws of motion. Until next time, see ya.